in this lecture, I'm going to talk about catalysis. So we have seen before in lots of different scenarios an energy profile of a reaction, with this being the reactant and this being the product, with increasing energy on this axis, and this one being called reaction progress. And so as we go from reactant to product, we go up over a hill, and that hill is the activation energy. Energy of activation. And we know that the rate constant is equal to a constant times e to the negative EA over RT. What this tells us is that as energy of activation increases, our rate will decrease. Because it's hard to get up and over the hill, so it takes more time the bigger the hill. And so if we catalyze a reaction, what we do is we lower that barrier. The reactants and the products still have the same energy, but the energy of activation for our catalyzed reaction is lower. And therefore, it takes less time to get up and over that hill. But where does this come from? Who came up with this graph? What is reaction progress? These are all kind of hand-wavy things. But if we start to look at what this really is, we have to start from the basics, from the energy of a single molecule. So let's take H2O. And let's say that this is an energy well that this molecule exists in. And as you go up in the energy well, you get more vibrational energy in the bonds. So the higher you go, the more reorganized the bond is, the longer it is, and the weaker it is. And so, if we put on this axis bond reorganization, we can see that as you go up in energy, the bond becomes more disorganized and reorganized, and that it's long and weak, and starts to not really resemble anything like a bond at all. So every molecule exists in an energy well, and things that look similar exist close to each other in reorganizational space. So that's what this axis is down here. It's this reorganization, this change. And if we go up and imagine that this is our H2O, and this is something that looks like H2O, OH minus. And say that we went out on one side of the H2O curve to where we're pulling one side of the bond all the way off. So one's kind of a normal bond, and one is a super long bond. So this is a very high energy state. This distance between these things is not favorable, and that's why we're up here in this high energy area. And it happens to be that this super high energy state of H2O looks exactly like a super high energy state of OH minus. And so there's this overlap in reorganizational space for them way up here at high energies. So if we're going to do a chemical reaction, what happens is we start at the low point here and we travel up the curve and across, and that's where you get your reaction profile. And that's why this dimension is always reaction progress, because we're trying to get from one well to another, and that's what these energy profiles come from. And here, we don't have to go all the way up to the cross. It actually starts to blend a little bit, and so we get to jump across and take a little shortcut. But this is basically a reaction of H2O going to OH minus plus H plus. So these energy wells are where this comes from. And when we think about catalysis, it's really an effect of other energy wells and moving them around. So imagine we had this energy well and it was overlapping with another molecule that has pretty much the same energy. In order to get across this, we go up and over and down. All right, we go from species A to species B. Well, what if B changed where it was in reorganizational space and was slightly closer to A? Then, let's call this B star. It's not quite the same thing as B because it's not quite in the same place. But in order to get to this B, we go up and over, and we've gone through a much shorter, smaller energy of activation. And so it increases our reaction rate just by being closer in reorganizational space. And what that tells us is that if two things look more similar, it's going to be easier to get to them than something that's less similar, because the hill to get there is going to be smaller. And so, if we have a reaction and one of our species is, say, a chain of amino acids, and this is an ongoing chain here, you have a hydrogen, and it's being broken, and it's being turned into a free carboxylic acid is at the end of a chain, and so it's cleaving this peptide chain. Okay, so that chemical reaction, and in order to do that, we have to go up and over. And the way that catalysis works in this reaction is that something exists in between as an intermediate. And what that thing is it looks something in between this and this. So it lies halfway through in the reorganizational energy. And in this case, what this would look like is something linked to an enzyme. So it makes a link to the enzyme before it completely comes off. And so the high energy states that it has to go through for just the normal reaction look like this. It's halfway in between here and here, but it's a strange structure where we've got negative charges and crowding. And so that's why it's high energy, is because you're forming and breaking bonds all at the same time. And down here we have an intermediate that's occupying similar reorganizational space, but is actually a semi-stable state. And in order to get between here and here, we also have to go through high energy transition states. So this looks similar to this, but it's lower down here, and here we have another transition state that looks similar, but it's bound to both the enzyme and the free OH, and it's a mixture of those two. So our energetic profile for our catalyzed reaction in this case has two transition states. We represent those with double daggers, and we see double daggers, one for our uncatalyzed reaction and two for our catalyzed reaction. And even though we have more transition states, they're much lower energy because they're closer in reorganizational energy. So the important part is that we form an intermediate. And this is something that is semi-stable, right? So it's not as stable as this or this. It's a little bit higher energy, but it's a low. It's not a peak. It's a low point, and it can be inhabited by a semi-stable state, and we can cross through that in order to take a shortcut to our product. And so if we look at this the way that we've seen it many times before, we have our uncatalyzed reaction. And in our catalyzed reaction, it's not just a lower activation energy, it's also got peaks and valleys. And so we've got transition states in both cases that take a certain activation energy to get there. But we've got an intermediate here that we don't see in the normal reaction that allows it to go faster. And that is pretty much how most things are catalyzed. Is through something existing in between, which is a very powerful concept, and biology and chemists have been using it for years alike. Thank you for listening.